Everything is made of atoms. Your chair, the air, my dog, the sun, my ring, and the most distant galaxy in the universe, all just atoms. This revelation is relatively recent. The mere existence of atoms has only been established for about a century, and a quantitative model for their behavior is less than half that old. What I will describe here is the modern atomic model, starting with macroscopic substances with which you're familiar and peeling back the layers until we reach the fundamental constituents of the atoms themselves, leptons and quarks. The forces operating within the atom determine its structure, while the arrangement of its various constituents can change spontaneously or via external intervention, producing light, telling time, and generating the enormous variety of substances that make up the world around us. The first discussion of the basis of matter in the Western world, at least, occurred in classical Greece. Democritus, who lived from 460 to 370 BC, and his teacher Leucippus were the first to offer the opinion that every substance has a smallest individual and, in their minds, indivisible unit, which they called an atom, atomos, which means indivisible. In their picture, each substance had its own unique type of atom. So there was a red silk hanky atom and a gray suit atom, and an air atom and a fingernail atom. This model is somewhat inelegant, as it lacks any explanatory power and doesn't even address the issue as to whether different atoms combine with each other. It just asserts that atoms exist. However, it did mark the first suggestion that there is a smallest unit of matter below which one cannot go. Aristotle, about 50 years later, viewed the world in a much simpler and in some sense more elegant way as composed of 5 different substances that he called elements: earth, air, fire, and water in the terrestrial realm, and the 5th element, ether, which comprised the perfect and unchanging celestial sphere. He posited that the properties of substances are defined by the different amounts of each element it contains, and change occurs by adding or subtracting one of the 4 elements to a substance. Progress on the fundamental structure of matter was then effectively suspended in the West for about 2,200 years. The medieval alchemists never did manage to change lead into gold by adding a little fire, as Aristotle's model would suggest. In the Enlightenment in the 18th century, however, the notion of experimentation was brought to the study of the subject of matter at its smallest scale, and many new substances were uncovered. Around 1800, the subject of chemistry per se can be said to have emerged. Chemistry comprised of the study of how substances combine to form new substances. The first task was to determine whether any substances were fundamental in the sense perhaps that Democritus would have it, things that we classify today, using Aristotle's word, as elements. The first 5 elements were known in prehistoric time, and they are the metals that are easily separable from the compounds in which they're found: gold, copper, iron, lead, and silver. Over the centuries, up until 1750, there were 11 more elements that were discovered, for a total of 16 prior to 1750. And then progress accelerated. Between 1750 and 1800, another 18 fundamental substances were identified. Hydrogen, for example, first isolated by Cavendish in 1776, and named by the great French chemist Lavoisier in 1783. Oxygen was isolated by Priestley in 1774. He had a rather unusual name for it. He called it dephlogisticated air, because he had this elaborate theory based on his experiments with substances acting inside sealed glass jars. He burned candles in these sealed jars, and he even introduced little mice into these sealed jars. Eventually, the candle went out, and the mice would expire. His notion was that somehow this process of burning or breathing was contaminating the air in some way, and therefore oxygen was a way of decontaminating the air. Lavoisier continued his experiments in Paris, and in 1780, identified this as a fundamental substance that composes air, not as some process. Carbon was identified by Lavoisier in 1789. It, of course, had been known for years as the substance graphite, but he recognized carbon as a unique and individual element. 1807, Davy, passing electrical currents through the mineral potash, discovered an element, potassium, that could not be broken down further, and the following year he found the element strontium. Between 1800 and 1869, there were another 29 elements discovered. So there was a total by 1869 of 63 elements known, and the Russian chemist Mendeleev arranged them into a table, the table we still use today called the periodic table, where he grouped elements that had similar properties when they combined with other elements into columns. This allowed him to make predictions of atoms not yet discovered. A model that makes predictions is the essence of modern science, and chemistry thereafter progressed rapidly. Some of the most common elements were not discovered on Earth. Indeed, helium was first discovered in the Sun in 1868 by Pierre Janssen. Helium coming from the word helios, the Greek for sun. It wasn't until 1894 that the second of the noble gases, the substances that don't undergo chemical reactions, was identified by Rayleigh, argon. And he did it by removing all the oxygen and the nitrogen from air through chemical processes and was left over with another gas, which he identified as argon. By 1900, physicists adopted the idea of atoms. Before that, they had been skeptical of their chemists' colleagues' experiments, but by the latter decade of the 19th century, they became to believe that there was a smallest unit of matter and that there were a set of elements that were unable to be broken down further. Physicists thus started studying the internal structure of atoms. But this is not a history of science, but rather how science reads history. So I will jump now directly to our modern picture of the atom. This modern picture includes the following features. First, atoms are tiny, inconceivably smaller than Democritus would have had them. As I said last time, it takes 25 trillion of them to cover the head of a pin. 50 times that many on the surface of my thumbnail. Today we know there are 92 distinct types of naturally occurring atoms, the modern elements. Notice we adopted both Democritus's term atom and Aristotle's term elements for these basic kinds of matter. Atoms are not, as originally envisioned, indivisible, but are in fact complex systems whose internal structure defines their properties. Indeed, for most of this course, we'll be focusing on the nucleus of the atom, a very tiny part of it, which will lead to most of our insights into history. At the macroscopic level, and let's start there because that's the world we're familiar with, matter is usually described as being in one of 4 different phases, which differ only in how the basic constituent particles interact with each other. Most things in the world around us are solids. This table, my hand, and these 2 oranges, which will, for the moment, stand in for atoms. In a solid, the particles that make it up, be they atoms or molecules, are physically touching each other. This makes solids incompressible. I can't squeeze this table and make it any thinner because the atoms that make it up are physically in contact with each other and there's no place for them to go. The particles are held in these fixed positions rather rigidly, but they are free to vibrate, and they vibrate in place up and down and back and forth like this. The average energy for each particle is relatively low. The next most common form of substance that we interact with every day are liquids. In liquids, the particles are also touching each other. You can prove this to yourself if you don't mind getting wet by trying to compress the water in a glass. You can't because, again, the particles that make up the water, the H2O molecule, are actually physically in contact with each other, and there's no way to squish them closer together. However, unlike in a solid, they're not rigidly locked in place, but they're free to slide over each other and move around, so they can migrate amongst their fellow atoms, although they are still touching. This phenomenon is made obvious by the fact that the water in this pitcher is in a high column, but I can pour it into this bowl and make it a flat distribution because of the freedom of the particles to slide over each other. Liquids take the shape of their container. The third common form of matter with which you're familiar is a gas. The air in this room is a gas. There's a very big difference between gases on the one hand and liquids and solids, because in gases, the particles are not touching each other. In the air in this room, if the atoms were the size of these oranges, there would be about this far apart, about 10 times their own diameters. The particles interact through collisions, rather like billiard balls. So the air molecules in this room, as I stand here, are running around, bouncing off each other in different directions, exchanging energy, but not affecting each other internally in any way. The average energy per particle here is higher because the atoms are free to run around. As you know, if one wants to go from the solid to the liquid to the gaseous state, all you have to do is add energy. For water, the one substance which commonly comes in all three phases in terrestrial conditions, if you have an ice cube, which is a solid, where the rigid atoms are locked in place, vibrating slowly, and you want to turn it into a liquid, that is, break the bonds and allow the atoms freedom to roll around each other, all you have to do is warm it up, add heat, which is energy. And if you have a liquid sitting in your teapot on the stove, and you want to warm it up and turn it into a gas, that is, make it boil, break the bonds that hold them together, and have the atoms running around freely, again, all you do is heat it up. You simply add energy. In fact, it turns out that most of the universe is in a fourth state of matter, none of those three we've just discussed, and one that doesn't exist on the surface of the Earth in most instances, called a plasma. Stars are made of plasma, the space between the stars is full of plasma, and even intergalactic space is mostly plasma. In plasma, not only are the atoms not touching each other, but the atoms themselves are torn apart. An atom consists of a positively charged nucleus, as we'll learn, and a little electrons that run around them like this. In a plasma, these two constituents of the atoms are ripped apart, and they run around completely independently of each other, bare nuclei and free electrons. The particles are very widely spaced, and they interact through glancing encounters, not actually colliding with each other, but attracted to each other, negative and positive, boomeranging around like this. The heavy particles moving relatively more slowly, and the light particles, the electrons, moving very rapidly, interacting like boomerangs. The average energy per particle in a plasma is very high. The temperatures are millions to billions of degrees. Every substance has a smallest unit particle. In that sense, Democritus was correct. And that unit displays the chemical properties of that substance. If this unit consists of a single atom, then it's classified as one of the 92 elements. But if it consists of two or more atoms linked together, it's called a molecule. Molecules can consist of two or more identical atoms or a combination of different atoms. A molecule can range in size from a simple pair, like the oxygen atoms and the nitrogen atoms, which running around in the air here are joined together in pairs, up to tens of thousands of atoms, such as the DNA molecule, which encodes our life. The atoms in a molecule are held together by electromagnetic forces, the unequal distribution of positive and negative charges, which makes the two atoms attract each other. A normal atom, or molecule, has exactly the same total number of positive and negative charges, and so is neutral. However, if an atom loses one or more electrons, or in some rarer cases gains an extra electron, it is called an ion. Its charge balance is disrupted, and this alters its behavior significantly. Now, as I mentioned, each atom is not a single thing, but a complex system, consisting of a nucleus that contains more than 99% of the mass of the atom and all of its positive charge, and the electrons which orbit the nucleus to provide the balancing negative charge. Now remember from last time when we discussed the scales of things, this picture that I'm drawing here and the one that you see in most textbooks is highly misleading. If the nucleus of the atom is the size of the orange, then this little electron in the first orbit will be about 5 city blocks away. The atom is almost all empty space, but it's held together by the electromagnetic attraction between the negatively charged electrons and the positively charged nuclei. This is the picture of atoms one gets from a high school chemistry class, and we'll use this picture some throughout these lectures. But the focus will be on the orange. The focus will be on the nucleus of the atom, because most of our clues to the history of human diet, of Earth's climate, of the formation of the solar system, and of the universe itself is written in the patterns of the nuclear particles. And the clock, which allows us to write this history, comes about because of changes in the atom's nucleus. The nucleus itself is a complex system consisting of 2 different components. Protons are the positively charged particles that give the nucleus its positive charge, and their number defines the type of atom that it is. Neutrons, the other particle, are very similar in mass, fraction of a percent heavier than a proton, but have no electric charge. They're in the nucleus because they add glue to help hold these positive charges together, which otherwise would want to fly apart. The number of neutrons per proton varies amongst the atoms, but their ratio is never very far from 1. We'll see in Lecture 5 how an unbalanced ratio of neutrons to protons leads to the clock that provides our record of history. The nucleus is held together not by electromagnetic forces, indeed that would tend to make it fly apart because of all those positive charges packed so closely together, but by an even stronger force which overcomes this repulsion, called the strong nuclear force. The strong force is communicated by little particles called gluons and bosons, which we'll talk about next time. The nucleus will turn out to be this invaluable clock, while the electrons jumping between orbits around the nucleus are essential for identifying which atoms we're dealing with, either in the lab or clear across the universe. Neutrons and protons are not the ultimate particle either. They're composites composed of even more basic units we call quarks. Quarks is a rather peculiar word, invented by Murray Gell-Mann in 1963, when it was recognized that there was some internal structure to the protons and neutrons. He writes about this by saying that he was one day perusing Joyce's Finnegan's Wake. I find it a little hard to believe that a nuclear physicist sits around perusing Finnegan's Wake on a regular basis, but nonetheless, looking for a word to define what these even smaller particles were, he came up with the nonsense word quark, thinking it sounded a little bit like the quark of a duck. In Finnegan's Wake, there is a line, and a little bit of doggerel there, which says 3 quarks for muster mark. Now, in Gell-Mann's model, there were 3 subparticles that make up each proton and neutron. So there the triplet was found in the quote. The section of the book was about a publican, someone who ran a public house, and as a consequence, Gell-Mann imagined that perhaps this 3 quarks for a muster mark might have really been a translation of 3 quarts for Mr. Mark. And so he adopted the quark or quark pronunciation of Q-U-A-R-K. The proton consists of a triplet of these quarks, 2 up quarks and 1 down quark. Now, up and down here are nonsense phrases as well. Perhaps better to think of them as U and D. They're just labels for different types of quarks. The proton is 2 ups and a down, or 2 U's and a D. The neutron consists of a triplet, also 2 downs and 1 up, or 2 D's and 1 U. This is the deepest level of matter that we've yet plumbed. And yet it leaves us in the uncomfortable position of having 24 fundamental matter particles, plus 6 messenger particles which communicate amongst them. It doesn't actually sound like we've made progress from Aristotle. He only needed 5 basic units of matter. Unfortunately, Aristotle was wrong. We will see as we continue to probe into the atom whether we have yet reached the most fundamental level. But our model today consists of these 24 matter particles and 6 messengers. The quark family portrait consists of 3 generations of 2 quarks each. They all have rather silly names. Up and down, the ones that make up our familiar protons, strange and charm, and top and bottom. Or sometimes originally, truth and beauty, T and B, S and C, U and D. The first member of each of these generations has a charge of plus 2/3 that of the electron. And the second member has a charge of minus 1/3. Thus you can see how a proton and a neutron come to be. A proton is 2 U quarks, plus 2/3, that's 4/3, minus 1/3 for the D quark, making a positive charge of plus 1 and perfectly balancing the charge on the electron. The neutron consists of 2 Ds, minus 1/3, so a total of minus 2/3, plus 1 U, plus 2/3, minus 2/3 plus 2/3 is 0. The neutron has 0 charge. Now each of these sets of quarks, all 6 of them, has an antimatter twin, which has the opposite charge, yielding a total of 12 quarks altogether. Under current conditions, quarks are never seen alone. They are always bound up, either in pairs, making particles called mesons, which we'll encounter later, and triplets, like the proton and the neutron, which as a class are called baryons. Now, there's a parallel set of families, the lepton family portrait, which mirrors the quarks in structure. It also contains 3 generations, each consisting of 1 light particle and its accompanying ghostly subatomic particle called the neutrino, plus each of their antiparticles. The first generation consists of the electron and the electron-type neutrino, and their 2 antiparticles. The positive electron, again the antiparticles have the opposite sign, which we sometimes call the positron, and the antineutrino that goes with it. The second and third generations consist of particles which are highly unstable in the universe today and fall apart very rapidly, so we don't encounter them in the refrigerator. They're called the muon and the tau particles, along with their respective neutrino types and the antiparticles of each. Neutrinos are very peculiar particles. They have an extremely low mass, a tiny fraction of the mass of the electron itself, 1/500,000th or so, and they interact very weakly with other forms of matter through the weak nuclear force. They interact so weakly, in fact, that neutrinos can fly directly through the Earth without even noticing that it's there. These will become important later when we try to probe what's going on in the centers of stars, where it turns out atoms are made. Neutrinos can send us signals where light cannot reach. Now, messenger particles are associated with each of the fundamental forces that govern the interaction of these constituents of the atom. The strong nuclear force is communicated by a particle called the gluon, which holds the quarks tightly bound together in their triplets, protons and neutrons, and spills over to help bind the nucleus of the atom, the focus of our study. The weak force, which allows nuclei to transform themselves spontaneously from one kind to another, essential in our clock keeping that we'll do throughout this course, mediates neutrino interactions and is communicated by 3 funny little particles with the unlikely name of intermediate vector bosons, the Z0 and the W plus and minus. The electromagnetic force acts on particles with electric charge, plus and minus, that we're familiar with, through the particle called the photon, which is also what we call light. And finally, the gravitational force is communicated between different bodies that have mass by a particle called the graviton. We'll explore all of these in more detail next time. Thus, our portrait is complete, with 24 fundamental particles and 4 sets of particles that communicate among them. It's important to get down the nomenclature here because we'll be using it throughout this course. We have a shorthand system to describe compactly the properties of atoms and molecules. Each element, each of the 92, has a 1 or 2 letter symbol. Let's take carbon because it's an atom that will have a starring role throughout the course. The symbol for carbon is simply C. And so that labels the element and tells us what kind of atom it is. To describe that atom, we associate that letter C with a couple of numbers. In the lower left, we write the atomic number. The atomic number is the number of protons. Simply put, the number of protons determines completely the identity of an atom. All 92, from 1 to 92 possibilities exist. For carbon, it's number 6 in the periodic table because it has 6 protons. And again, that defines completely its identity. So a little subscript 6 is put to the lower left of the element's symbol. To the upper left, we add a number that characterizes the mass of the atom, the atomic mass, which, all being concentrated in the nucleus, consists simply of the number of protons plus the number of neutrons, a simple arithmetic sum. In the case of carbon, as we'll see, there are different kinds. All have 6 protons by definition, but some of them have 6 neutrons, some have 7 neutrons, and some have 8. So carbon might be written as a C with a subscript 6 and a superscript 14, if it's the kind of carbon that has 6 protons and 8 neutrons. To the upper right of the atom, we indicate whether or not it's a neutral atom, which is the normal state of things, or whether it's lost or gained an electron. If it's lost an electron, the net charge on the atom will be positive, and so we'll put a little plus sign. If it's gained an extra electron, borrowed one for a while, we put a little minus sign. If we have a substance that's made of 2 or more atoms, the lower right tells us the number of atoms involved. For example, the carbon dioxide I'm breathing out as I'm speaking to you now consists of carbon, a C, and 2 oxygens, an O. We write that as CO with a subscript 2 in the lower right. Now, each type of atom, each element, comes in several varieties, which we call isotopes, iso meaning equal, which differ only in the number of neutrons they contain. The example that we'll see repeatedly in the course is, as I've said, carbon. Carbon always has 6 protons. That makes its identity. But it can have either 6 neutrons, 7 neutrons, or 8 neutrons. These would be written as carbon 12, carbon 13, or carbon 14. Since the atom's interactions with other particles in the world is determined strictly by its electrons, which you will recall are greatly distant from the tiny little nucleus out there city blocks away, they do the communication with the outside world. They, therefore, provide us with all of chemistry, where chemistry is talking about the interaction of atoms, whole atoms, with each other. The electron configuration, the number of electrons in various orbits around the atom, determine how it behaves in its interaction with others. Now, since an isotope always has the same number of protons, and therefore, in its neutral state at least, always has the same number of electrons, all isotopes of a given element are chemically identical. They interact with the world in exactly the same way. However, there is one crucial difference amongst the isotopes, and that, obviously, is its mass. The ones with more neutrons are heavier. And since heavier particles move more slowly than light ones, chemical reactions, the electrons way out there, sometimes discriminate against heavier isotopes because they take longer to catch up, to get to connect with another atom. This will become crucial in our study of the history of diet and of other historical features. Each element has an optimal number of neutrons to make its nucleus stable. Too large a departure from this optimal proton-neutron ratio will, as we see, make atoms unstable to radioactive decay. The interactions of atoms and their constituents, governed by the rules of the forces of nature, lead to all the properties of the material world. Now, this catalog of particles that I've just given you, that makes up everything in the world around it, is just that, a static list of things. But it's the interaction of these fundamental constituents, bumping and jumping and jostling and transforming, that produces change, progress, decay, the stuff of history. The book of accounts in which we record these changes has a single currency. It's called energy. And it's energy that we'll be exploring next time.